Greetings. I'm going to show you one of the craziest, most balmy things I've ever done. Well, not that balmy really. Well, it is, I suppose. It's kind of a daft thing. This is the 4D Systems Picadillo 35T. It's a 3.5-inch TFT screen with built into it... What is my camera doing? Built into it a chip kit, which is like an Arduino, only a little more powerful. This one uses the PIC32, 80 megahertz, 512k of flash, 128k of RAM. I will start by saying you can probably do this with just an ordinary Arduino with a TFT screen attached. I'm using this because it is so convenient to use it. An all-in-one system that you just plug in and use. Unfortunately, 4D Systems have discontinued them. They weren't selling well, which is a shame because they are such a fantastic bit of kit. But I guess the $90-odd price tag on them was a little bit steep for the average Arduino user. So unfortunately they're not making them now, except for specific runs for a customer who wants like 500 of them. But if we campaign hard enough with them, I'm sure they'll be able to bring them back. Anyway, this TFT screen, I've got so many TFT screens around that for ages I've been wondering, is there a way that I could use any of these little TFT screens as a monitor for my computer? Yeah, balmy, I know. So, yesterday I did it. I've been wanting to try this out for a long time, and I finally did it yesterday. I will also say that this can only really be done on Linux. You'll really struggle to do this sort of thing on Windows or even OS X. I mean, you can kind of do things like this on Windows, but you won't use it as an actual monitor in Windows. On Linux, though, thanks to a very clever piece of software that I stumbled across yesterday, it's a doddle. Okay, so what do we have? I'll just give you a quick tour of the Picadillo so you can see what we're playing with. Let's turn on the inspection light. Okay, at the heart of it is the PIC32 MX795F512L. 80 pins, plenty of I/O, lots of oomph. But for this project, the oomph really isn't necessary. It's got a speaker on it for audio, obviously audio, for PWM audio. FT232 serial interface, SD card slot, and of course TFT screen. And they are really nice TFT screens they use on these. And Arduino headers, of course, actual chip kit headers rather than Arduino headers, which means you get the double row, so you get twice as many I/O on it as you do in an ordinary Arduino, twice as many analog pins. But other than that, it's pretty much an Arduino. You program it with the same language. It's an Arduino to all intents and purposes, just a bit meatier. Okay, so we have at our disposal a serial connection over USB. And that's going to limit how much data we can do in a given time period. So we're going to have to come up with a clever way to reduce that amount of data. So if I want to display a screen, a whole monitor's worth of data, it's going to be a lot of data. And this is 480 by 320 pixels at 16-bit color. So that's, if I can quickly bring up my calculator. At 480 by 320 is 153,600 pixels. 2 bytes per pixel. We're talking over 300 kilobytes per frame of the display. the fastest I've managed to communicate with one of these is 2 megabits per second, which is pretty quick for a serial connection. So at 2 megabits per second, that's effectively 200 kilobytes per second. So already you can see that at 300 kilobytes and 200 kilobytes per second, it's going to take longer than a second to display a whole frame. That's not really going to be usable. So something else will have to be done. I shall come back to that in a moment when I describe the software that I've written. But the heart of the software is a system that I stumbled across yesterday. It was written, I think, by Freescale, called the Virtual Frame Buffer. Now, Linux has a wonderful video system called the Frame Buffer system. It's what's used on things like the Raspberry Pi, where you have a device on the file system called /dev/fb0, which is a file which the content is the video memory. It's a direct connection to the video memory. So if you open the file and write to a location on it, a pixel appears on the screen. I mean, how easy is that to use? No complicated APIs, no fancy programming. Open a file, write to it. You can also open the file and read from it. Now, that frame buffer is normally associated with an actual video card. But I've got NVIDIA cards on my computer, 2 of them actually, with 3 screens, and they don't normally provide a frame buffer interface. They're far too powerful for such a simple interface. They've got their own special API, drivers talk to them very fast. Gives you much better, faster frame rates, 3D options, all that sort of thing. The frame buffer interface is very basic, and because of that, it can be a bit slow. So most video cards don't use it, they don't touch it. But I've come across the virtual frame buffer, which gives you a frame buffer device. In fact, it can give you lots of frame buffer devices independent from a graphics card, which is great. So you can create a frame buffer without having a graphics card and do what you want with it. So I downloaded it, the code. I finally got it to compile, which was not easy. Not easy at all. Where are we? Virtual frame buffer driver. Let's switch over to my desktop so you can see. Here we go. Okay, the VFB driver is a very basic frame buffer driver that allows creation and management of an arbitrary number of frame buffer devices. This is a basic driver which allows the user to create n virtual frame buffers. These frame buffers are no more than contiguous physical memory regions that are wrapped by the standard frame buffer device interface. Now, they say it's as simple as typing make -c path to kernel sources m equals backtick pwd backtick. But I mean, yes, it is, but the hard part is getting that path to the kernel sources. On Ubuntu, the kernel sources and the kernel that you run are different versions. They do like to mess things up. I'm using, why can't I get me, there we go. I'm using kernel 4.15.0-36-generic. Now the kernel sources that you get, if you install the Linux source package, oops, it's Linux source are 4.15.0. But in actuality, the sources within there, let's just delete the old tree because I'm going to show you how to do this. Quite a large tree, so this will just take a moment. The sources in there are numbered differently. And these ones, I believe, are Linux source 4.15.18. Okay, so when you install the Linux kernel source package, all you get is that. You get a Debian, Debian master, and a tarball of the source. So first you need to extract that tarball. Hint, do it as root, because you can't write to that location. Quite a large tarball. This takes a few moments to extract. A lot of files in it. To the drivers. So what you're going to need to do is change the version number of the kernel sources to match the kernel that you're using. If you don't, when you try and load a kernel module, it says, nope, this is a different version. I'm not having it. The kernel module number and the kernel number have to match precisely. And that's kind of a bit of a headfuck, really. Why Ubuntu have decided to do this, I'm not entirely sure. It's probably to do with their patching system, where the kernel that Ubuntu provide is not the standard Linux kernel, but it's patched with various fixes and extra drivers and things like that. So they use their own version numbering for it. Still extracting. I'm going to put all the sources that I'm working with today, along with a few extra instructions, on a GitHub repo in a bit. I'll put a link to it in the description at the bottom. Check back later for that one if it's not already there. Okay, that's extracted. So now we've got a Linux source 4.15.0 folder. We go into there and I'll take a look at the make file. Yeah, this is version 4.15.18, which is also known as Fearless Coyote. But that doesn't match what we have, which is 4.15.0.36 generic. They're the same version internally, but the actual numbers are different. So we need 4.15.0-36-generic. So if we edit the make file and change these version numbers to match 4.15.0, the extra version is what goes on the end, which is -36-generic. Okay, now the numbers should match. The next thing we need to do is to prepare the kernel sources. First, we need to create a configuration, which is as easy as make old config, which copies the current running configuration into this kernel sources. Just hit return on any extra drivers that have appeared since this kernel source was compiled. Then we need to prepare it. Make prepare. That builds various scripts which are used during the compilation. My CPU is being absolutely hammered at the moment with all the video work that's going on in the background. So compiling is a little slow. There we go, almost done. There we go. And then we need to prepare it for compiling modules, which again is make modules prepare. Builds a few more scripts. And we are done. There we go. We have prepared the kernel sources ready for compiling a kernel module. Okay. Go back to our sources, and then we can type make -c user source Linux source, etc. Module m equals pwd. And there we go, it's compiled. Now, loading the kernel module is the same as any kernel module, but what I like to do is copy it into the kernel module tree. I put it into a specific location, which is lib modules 4.15.0.32 36 generic, isn't it? Yeah. Actually, we can use which is it? I can never remember which is the code for this. Kernel version is V. No, kernel R. There it is. So we want to copy the virtual FB KO to /lib/modules /backtick uname -r /drivers /video /fbdev. This should tell me that it's... No, did I do the right? I'm not sure I did the right folder there. Lib modules uname -r drivers. No. Oh, sorry, no, there's a kernel first, isn't there? Kernel drivers. Video. There we go, fbdev. Frame buffer devices. So that's the path that you want to copy the virtual FB file into. As you can see, I have actually already done that. And then you need to update the list of kernel modules that are available, which is simply depmod as root. And this takes a few minutes to run. What it does is it scans through all the kernel modules that are available and works out which other modules they depend on. Builds up a directory of them and all the links that are between them. There we go. And then you can use modprobe to load that module. In etc, you've got module modprobe.d. You create a file virtual_fb.conf. I think it matters what it's called as long as it ends with .conf. And put in there options virtual_fb VFB count equals and the number of frame buffers you want to have it create. I'm having mine creating 2. I only really need 1, but it's nice to have another one there just in case. You can never have too many. Well, I say you can never have too many. If you have too many, it'll start consuming too much kernel memory, and you may start running into memory problems with if you have like thousands of them. But I'm just having 2. And then it's as simple as modprobe. If I could type virtual FB. And then there's your frame buffer devices. Now FB0 is actually the frame buffer for the internal Intel card in my computer. It's not connected to anything, but it just creates it there anyway. FB1 and FB2 are my new frame buffer devices. Okay, now you can use a program called fbset to change the parameters of one of these frame buffers. -fb FB1. Now this one is currently set to 480 by 320 at 32 bits. They default to 128 by 128 at 16 bits. But I've reconfigured this one. It's actually my program that I'll show you in a minute that reconfigures it to the same resolution as the Picadillo, but running at 32-bit depth. You could run it at 24-bit, 16-bit. It doesn't really matter, but as long as the program that talks to it is expecting that same format. I've specifically chosen 32-bit because I'm going to be running an X Windows session on it, and that prefers it to be 32-bit if it can. Okay, so we have a frame buffer device, but that frame buffer device doesn't actually do anything. All it is a store of data. I go xxd/dev/fb0 fb1, sorry, pipe through head just to get the first bit. It's just data. That is, as it happens, empty. Okay. So, onto our program. A frame buffer can have an X Windows session running on it. I've got a configuration for an X Windows session to talk to frame buffer 1, specifically running at 480 by 320. You can start that with xorg. I've got the command written in the README here. Xorg -config where your configuration file is, -share VTS and -no VT switch. That allows it to share the same virtual terminal as your current desktop session, and no VT switch won't switch to this new configuration. If you don't have those, it'll mess up your current X Windows session and you'll lose your X Windows. And :1 is the screen number that we're going to allocate to it. :0 is your default normal screen session. :1 is the next one in the list, basically. You can use any number you like above 0. And that will start an X Windows session. I've already got one running on my desktop, on my frame buffer actually there. So I've also started a Window Maker session and Synergy. That's a way of getting my mouse and keyboard across to it. Very useful program, Synergy. It allows you to share your mouse and keyboard across multiple computers, multiple displays, as many as you want. It's a brilliant program. Okay. So I've got an X Windows session displaying on that frame buffer, but the frame buffer isn't doing anything with it. It's just accepting the screen data and storing it, basically. So next we need some way of getting that data out of the frame buffer, sending it over to the Picadillo and displaying it. So the next thing we need is a program running on the Picadillo. I've written a fairly simple system using Display Core. 2 megabit serial connection. The TFT running rotation 1, just ordinary landscape with the backlight on full. And a simple little state machine for reading the serial. Very simple packet format. Starts off with starter frame of hexadecimal 16 twice. A 1 for the start of header. 2 bytes for a block number. Now what I've done is I've divided the screen up into blocks. Each block is 8 by 8 pixels. And I transfer the image as those blocks. So I transfer 2 bytes for the block number, starting top left, progressing down to bottom right, scanning across. Then OX02 for the end of header, then 128 bytes of data for the actual content of the block as 16 bits per pixel, and then an OX04 at the end. Simple as that. Very simple, straightforward packet. Once a block has been fully received, it just dumps it to the screen. In the right location, of course. I shall upload this to the GitHub repository as well, so you can have a look at it. Doing the same thing on an Arduino will be slightly more tricky because you won't have Display Core, so you'd have to use your chosen TFT driver system of choice, U8glib or UTFT, whatever. But the basic principle will be the same. Read the packet and output the pixels to the screen. The great thing with the Picadillo, of course, is that the TFT screen is directly connected 16-bit parallel to the parallel master port of the PIC32, so it can update the data on the screen pretty damn quickly. I mean, we're talking probably about 10 frames per second, which is a lot quicker than you get off any Arduino. But when we're sending the screen data over serial, that's fairly irrelevant because the data's coming in so much slower than the screen can be updated. Okay, so that's our Arduino or ChipKit program. Let's upload it to the Picadillo using UX IDE, of course, the IDE of choice for the discerning Arduino user. Compiles so much faster due to its aggressive caching, and looks so much sweeter as well. uxide.org, download it today, don't delay, as Louis Rossmann says. Okay, that's now programmed in. Back to our terminal session. Okay, now on the PC side of things, a program which will read the display from the frame buffer and output those blocks through serial. A reasonably simple program. Written in C, you could do a similar one in Python using PySerial. The basic premise of it is open the serial port. Oh, actually, the very first thing it does is configure the frame buffer to the correct resolution and depth. Open the serial port, configure it for the right baud rate. Actually, the code that I've got here doesn't always work properly. There's a different version that I've got to dig out that works better. The problem with it is that it doesn't always like custom baud rates like this. So I've got a better version which I need to drop in. So I need to manually configure the baud rate first before running the program. I'll do that in a moment. A brief delay, 5 seconds. Like most Arduinos, the Picadillo resets when you open the serial port. The FT232 has the DTR connection connected to reset. So you open the serial port, it toggles the reset, runs the bootloader, allows you to upload, just like the Arduino Uno, etc. So we have a short delay just to get past the bootloader. Open the frame buffer as an ordinary file. Now, the clever part is using the mmap function. Now, mmap is memory map. It takes an ordinary file and maps it into memory. It's a fairly powerful and flexible thing. So instead of then sort of seeking to a specific location in a file and reading and writing from it using read and write, you just map it into memory and you have an array. And you just access the array and everything else is done for you. It's a brilliant system. So I have an array of 8-bit unsigned called FB, a pointer to it, so it's not actually got any memory assigned to it yet. And then I map the frame buffer FD into memory with the resolution times 4, because it's 32-bit frame buffer, so you've got 4 times the memory as you have pixels, 4 bits per pixel. And assign that to my frame buffer variable. And then I've got full access to the whole frame buffer as an array in memory. And the first thing I do is send every single block as a complete refresh of the screen. And then I have a system. It's very, very primitive at the moment. I need to rewrite it. It doesn't work particularly well, which keeps track of checksums for each block. For every block, I go through and I calculate a crude checksum. At the moment, all it is just the sum of the colours of all the pixels. 16-bit values for the pixels in RGB 565 form. Added together into a 32-bit variable. If it overflows, it overflows. I really don't care. And I use that as a checksum. It's crude. It is very crude, and it doesn't always work. I mean, it works, but it doesn't always create a unique number. And what I really want is a unique number. So every 10 milliseconds, I scan through all the blocks, all 2,400 of them, looking for any blocks that have changed. As soon as a block has detected as changed, I send it up through serial. The checksumming routine, here we go, is, as I say, simply going through each pixel, 8x8 pixel, of each block, getting the pixel colour in a 16-bit form, which is this little routine here, get pixel, which takes the red, green and blue and crops them and shuffles them around to create a 16-bit value. Take each pixel in 16-bit, add it to the checksum and return the checksum. Simple. Doesn't always work, but it's a crude proof of concept method that gets it going. And if it detects the change, it sends the block. Sending it is as simple as building up the same header as before, 2 starter frames, start of header, the 2 bytes of the block number, end of header, send the data, all 128 bytes of it, that's 64 entries of 16-bit, fill it up with the pixels, send it, end of text, write that header, and that's it basically. Just keep doing that over and over and over again. As soon as anything's detected as being changed on the display, it updates that block. Gives a reasonably quick response time, minimal data, and it actually becomes usable. So let's get it going. I switch back to... Where's my controls gone? Switch back to my desk shot with the picadillo on it. Okay, actually let's turn off my inspection light. So I've got my sketch running on there. I need to then run my screen server program. And if all goes well... I bet this isn't going to work now, is it? Oh, I know what I forgot. I forgot to set the baud rate, because I said just now the serial code that I'm using is inferior and doesn't actually work properly. It doesn't set the baud rate. So I need to go wrong screen, stty minus f /dev /tty USB 0 speed 2 million. Okay, let's just check that did change. Yep, speed is 2 megabits. Okay, so now I run my screen server program. 5-second delay to let the bootloader pass. There we go. Oh, screen's upside down at the moment. But there is X Windows with Window Maker running on it. And thanks to Synergy, I even have mouse cursor and keyboard. Let's bring this into a closer view with my inspection camera. My mouse gone, there it is. Let's turn that light off. Not the greatest of camera this, but you get the idea. There we go. One 3.5-inch TFT screen, PIC32 controlled, with X Windows being displayed from my computer. It's fully functional. Bit slow when you've got large changes. And the mouse does tend to disappear off the top sometimes because it's so much smaller than my main screen. But you can do everything on it, albeit slow and tiny. Linux system displayed on tiny little PIC32 serial connected screen. And as you can see, when you've got only sort of small changes, get my mouse cursor back on the screen, such as here. Oh, of course, it changes the mouse, doesn't it? Such as the use my finger. Or better still, let's use Prodigal. There it is. Such as here, is a reasonable frame rate you get from it. Now, the problem with the checksum is when you get a display like this. This CPU level monitoring display consists of a red line going straight across, and that basically goes up and down. Now, an 8x8 block covering that red line is just all black apart from 8 pixels of red. So the black pixels added to the checksum are 0, so they don't affect the checksum at all. The only thing that affects the checksum is the red line. As those 8 pixels move up and down, they're still 8 pixels. So regardless of where they are in that block of 8x8 pixels, it's still 8 pixels of red. So the checksum will always be the same. So I do find that this CPU monitor widget doesn't always update properly. And for that I need to develop a better checksum. There's probably a much neater system I could use, a CRC32 or something. But for now, for testing that it works and for showing it off, it's adequate. So there we go. There's not really a lot more I can say about it. I'm going to upload it to the Tinterwebs onto GitHub. I'll put the link in the description below. And I hope you found it interesting and somewhat stupid, really. What would you use this for? I guess I could have it displaying just a whole bank of these kind of widgets for monitoring my computer, but well, it's a bit slow, it's a bit heavyweight. It would be better using a chip kit with a dedicated USB connection rather than FT232. Probably an MZ chip, PIC32 MZ chip with the high-speed USB connection. 480 megabits supposedly, but you never get that sort of speed out of it because the chip's only running at 200 megahertz, so there's no way you can do 480 megabits of processing. But it would certainly give a more fluid connection. Also, using HID instead of CDC ACM, for example, would make the packet processing a lot easier because it's actually sent up as packets. But for a quick prototype, you can't beat the Picadillo 35T. I just wish they were still making them. Well, thank you very much for watching, and I hope you enjoyed it. Don't forget to subscribe and like this video, because subscriptions and likes are the currency of YouTube, for what it's worth. I don't really give a monkeys, so yeah, don't bother subscribing, don't bother liking. I tell you what, dislike it. Let's see how many dislikes we can get on it. See if we can get to the record of dislikes. Thanks again. Cheerio.